We're going to continue tests for convergence or divergence of infinite series. The integral test. If f is positive, continuous, and decreasing for x is greater than 1, and a of n, some sort of series numbers, is equal to f of n, some function, then the series and the integral, as shown, will either both converge or both diverge. They will either both converge or both diverge. Let's take a look at example 1. We're going to apply the integral test to determine convergence or divergence of the series integral from, series sum of n equals 1 to infinity of 1 over n squared plus 1. We're going to note that we're going to make a sub n equal to f of n. And so we're going to take this and basically make it look like f of x equals 1 over x squared plus 1. Now we have to make sure that the conditions are true. So you have to actually write this stuff down and check. Is f of x, which we have defined as 1 over x squared plus 1, is it positive, continuous, and decreasing? For all x is greater than or equal to 1. Well, for all x is greater than or equal to 1, that is positive, it is continuous, and it is decreasing. So that means that we're allowed to use the integral test. So because we're allowed to use the integral test, we can say the integral from 1 to infinity of 1 over x squared plus 1 dx is equal to arctangent of x evaluated from 1 to infinity, which I should probably be a little bit more careful and say the limit as a goes to infinity and change this to an a, so I should be a little bit more proper here. So the limit as a approaches infinity of arctangent, so that's the limit as a approaches infinity of arctangent of a minus arctangent of 1. Arctangent of infinity is basically pi over 2, and arctangent of 1 is basically, well, it is pi over 4. So this is pi over 4, which is a number, so that means the series converges. Therefore, the sum from n equals 1 to infinity of 1 over n squared plus 1 converges. So we applied the integral test, we checked the conditions, and then we actually did the integral and we showed that it converges. Problem 2, explain why the integral test does not apply to the series 2 plus sine of n over n. We would have f of x equal 2 plus sine of x over x, and this function is always positive from 1 to infinity. It is continuous, but it is not always decreasing. And you can tell because sine is an oscillating function. And since sine is an oscillating function, that means it's not always going to be decreasing. And if we look at it, it is positive for all values greater than 1, but as you can see, it is not always decreasing. There are periods of time where it is increasing. Test number 2 that we're going to talk about, the alternating series test. We're going to let a sub n be greater than 0, then the alternating series, the sum from n equals 1 to infinity of negative 1 to the n, a to the n, or a sub n, and the same thing with n plus 1. So it doesn't really matter whether the first or second or whatever terms are positive or negative, as long as all of the alternating terms are alternating between positive and negative. Then we have convergence if the following 2 conditions are met. As long as a sub n is greater than 0 and a sub n is greater than or equal to a sub n plus 1 for all n bigger than or equal to some capital N where capital N is an integer. So let's explain that one for a second. So when we say a sub n is greater than 0, what we mean by that is that because this -1 to the n term is alternating back and forth, that means we actually need all of these terms to be alternating back and forth. So that means these a sub n's have to be positive, so then the -1 to the n ends up making the series alternate back and forth between positive and negative. If a sub n was flipping back and forth between positive and negative, then the -1 to the n wouldn't really make a difference. And we also have to have each successive term, so that means a to the n plus 1, has to continue to be getting smaller and smaller after some point. It doesn't have to keep getting smaller at the beginning, but after some point, and it doesn't matter where, but let's say after the 50th term or after the 100th term or even after the second or third term, at some point, it has to constantly be getting smaller and smaller and smaller, or else it doesn't really work. So that's condition 1. Then condition 2 is that the limit as n approaches infinity of the successive terms is equal to 0. So let's do some examples. Example 1. We have the sum from n equals 1 to infinity of -1 to the n plus 1 of 1 over n, or times 1 over n. So let's take a look at this. We can say that a sub n is greater than or equal to a sub n plus 1 for all. You may see this mathematical notation somewhere. I'm going to use it throughout the video because it's a lot easier for me to continue to do that. It's an upside down A. That means for all. Okay, so for all n greater than or equal to 1, we know that's true because if n is 1, that's greater than or equal to 1/2. And then we have 1 over n for all n continuing is definitely greater than or equal to 1 over n plus 1. So that works for all n greater than or equal to 1. Then let's take the limit. So the limit as n goes to infinity of 1 over n, that is equal to 0. Now we know that the series 1 over n diverges. But that's not part of this test. It doesn't ask us whether this particular series converges or diverges. All we need to see is that the limit of that, of this part of the series has to go to 0. And so because that's true, then therefore, by the alternating series test, the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over n converges. So that is true. Okay, next one. If we look at this, we'll take a look at the conditions. Is a sub n greater than or equal to a sub n plus 1 for all n greater than or equal to something? So if we take a look at this, n plus 1 over n, is that greater than or equal to n plus 2 over n plus 1? That is true, actually, for all n greater than or equal to 1. So the first condition holds. If you take a look at this, you could actually do some solving here to show that it's true. If you cross multiply, you get n squared plus 2n plus 1 is greater than or equal to n squared plus 2n. And if you subtract everything, you get 1 is greater than or equal to 0. So that is something that you can actually show is true for all n greater than or equal to 1. However, when we take a look at the limit as n approaches infinity of n plus 1 over n, that's equal to 1, which is not equal to 0. Therefore, the alternating series test diverges. Absolute and conditional convergence. So occasionally, something may not be an alternating series, but it still has positive and negative terms. If we have this situation, then what we want to do is we want to determine whether this series can actually has a specific type of convergence, which we call absolute convergence. So if we look at sine of n over n, we look at that series. it has both positive and negative terms, and it's not an alternating series. Um, so it doesn't follow a specific pattern where every time we plug in another integer, we get positive, negative, positive, negative. Sometimes it's positive, sometimes it's negative. One way to obtain information about this is we look at the absolute value of the series and see if that converges. So if the absolute value of the series converges, then we have something called absolute convergence. So if we're looking at this particular situation, if the series, the sum of the absolute value of a sub n converges, then the other series definitely converges. That is a true statement. So this series, the sum of a sub n, is absolutely convergent if the sum of the absolute value of the terms converges. It is conditionally convergent if the sum of the terms converges, but the sum of the absolute value of the terms does not converge. So things are absolutely convergent if part 1 is true. They're conditionally convergent if part 2 is true. So the biggest example that's really easy for us is the sum from n equals 1 to infinity of 1 over n. That series diverges. But if I change this to -1 to the n over n, that converges. So if I look at this, this would be what we call a conditional convergence. Because if I took the absolute value, I just get the harmonic series, which diverges. But if I get rid of the absolute value, then this conditionally converges because I know that the alternating harmonic series converges, which we learned in the previous lesson right here. That's the alternating harmonic series. Okay, so if we're taking a look at this, that's the difference between absolutely convergent and conditionally convergent. So let's take a look at some examples. Number 1, the sum from n equals 1 to infinity of -1 to the n times n factorial over 2 to the n. So first of all, n factorial, we need to remember what that is. That's n times n minus 1 times n minus 2 times ... all the way down to 1. So if I take a look at, let's say, 8 factorial, that would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So in case you forgot what that was, that's what it is. So if we take a look at this, the first thing we are going to want to do is we are going to want to, we're probably going to want to look at the absolute value of this. So if we take a look at the absolute value of this, that would be n factorial over 2 to the n. Because if I take the absolute value, basically all that's going to do is turn the -1 alternating into constantly being positive. So if I take a look at this sum, that's definitely going to diverge because if I take the limit as n goes to infinity of n factorial over 2 to the n, n factorial grows way faster than 2 to the n. And I'm just going to show you that so then you can see that it's true. So x factorial, it does some weird stuff when you have negative values. But if you have positive values, it grows. It looks like for short periods of time, 2 to the x or 3 to the x or whatever is bigger, but then there's some kind of intersection point. And at some point, it always shows up somewhere. And it's usually really high up for the y's, but not that high for the x's. So at some point there's an intersection. And see how by 6, 3 to the x is overtaken by x factorial, and it's a really high value of y, so I'm not going to continue doing this. But factorial always beats exponentials in the long term. So factorial is actually the biggest thing that we deal with in this class. It's bigger than exponentials even in the long term. So as n goes to infinity, this is infinity, and therefore this is not going to work. That also means that the alternating series test won't work on this because the limit of our a sub n term does not go to a number, or it doesn't go to 0, and so therefore this series diverges. Now let's take a look at number 2. We can already tell this does not converge absolutely because by the integral test, 1 over x to the 1/2, which is equivalent to 1 over square root of n, or 1 over square root of x, that is continuous, decreasing, and positive. Continuous, positive, and decreasing. And we know that the integral from 1 to infinity of 1 over x squared or 1 over x to the 1/2 dx, that diverges by the p-series test. Or we can just say by the integral, or by the series p test, we know that that diverges. So there are a ton of different ways that we can say that that diverges. So because of that, we know this will not converge absolutely. Sorry, my handwriting is terrible here. So that will not converge absolutely. So now we can see if this converges conditionally. And so we can see if this converges conditionally by the alternating series test. We know that by the alternating series test, what we need is we need a sub n to be greater than a sub n plus 1, and all of our terms to be greater than 0 after a certain point. And so we can say 1 over square root of n is greater than 1 over square root of n plus 1. That's true for all n greater than or equal to 1. So that works. And then if we take the limit as n goes to infinity of 1 over square root of n, that does equal 0. So therefore, this converges conditionally. Now let's take a look at number 3. We have negative 1 to the n times n plus 1 over 2 over 3 to the n. So the first thing we have to do is figure out what in the world is going on with that and why we would even put that there. So if we take a look at it, n times n plus 1 over 2, let's just take a look at a couple terms and see what's happening. If I plug in 1, I get 1 times 2 divided by 2, which is 1. If I plug in 2, I get 2 times 3 divided by 2, which is 3. If I plug in 3, I get 3 times 4 divided by 2, which is 6. If I plug in 5, I get 3, my bad. If I plug in 4, I get 4 times 5 divided by 2, which is 10. So if I'm looking at this, I had a couple odds, a couple evens. It appears that there's not going to be any specific alternating between positives and negatives, but I will have some positive terms and some negative terms. So in that case, let's take a look at the absolute convergence, so then I don't even get confused with whether it's going to be positive or negative. So if I take a look at this, does the sum from n equals 1 to infinity of 1 over 3 to the n converge? And if I take a look at that, that is a geometric series, and I can look at the geometric series test, and I can say that this does converge. So because the absolute value of this converges, and I'm not going to go through all the steps, but because Mrs. Casey did that, but because this converges, therefore I can say that the alternating one converges too, and so this has absolute convergence. it converges absolutely. That implies conditional convergence. So if it converges absolutely, it also converges conditionally as well. There are another couple tests that we have. One more test for absolute convergence is the ratio test. So if something converges with the ratio test, it also converges absolutely. So let's take a look at this. Let the sum of a sub n be a series with non-zero terms, and we're going to constantly be looking at the limit as n goes to infinity of the ratio between the next term and the previous term. We're going to say that the ratio of those things, the limit as n goes to infinity, that equals L. Okay? So the sum converges absolutely if L is less than 1. The sum diverges if L is greater than 1. And the ratio test is inconclusive if L equals 1. And we can do a really quick example of why L equals 1 makes the ratio test inconclusive, because if you have the series 1 over n or the series 1 over n squared, both of those have L equals 1. I'm not going to show it, but both of those have L equals 1. We know this one diverges, and we know this one converges. So that is an inconclusive test. All right, let's take a look at this. We're going to do the ratio test on all of these. So we have to make sure that we have non-zero terms. So clearly all these terms are non-zero. So if we take a look at this, we're going to take the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial. So now it just becomes a lot of canceling stuff out. So I'm going to take the fraction in the denominator and rewrite it as it's part of the numerator. So this n factorial goes to the big numerator, and this 2 to the n goes to the top denominator. My fault. I need to write a limit here. So the limit as n goes to infinity, when I cancel stuff out, 2 to the n plus 1 divided by 2 to the n is just 2. And n factorial over n plus 1 factorial, if I think about what these things are, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 times dot, 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 all the way down to 1. N factorial is the exact same thing, except it starts right here. So because that's true, when I have n factorial and n plus 1 factorial, everything from n and beyond cancels out, so I'm just left with n plus 1 in the denominator. So if I take a look at this, the limit as n approaches infinity of 2 over n plus 1, that is equal to 0, which is less than 1, which is my L. So because that's true, this converges absolutely. If you need that more, pause the tape because I'm erasing it. Okay, number 2. This series, we're going to take a look at the ratio test. Notice we have a bunch of non-zero terms. So I'm going to replace all my n's with n plus 1. So I have n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1. That's all over n squared times 2 to the n plus 1 over 3 to the n. And we're taking the limit as n goes to infinity. So when I rewrite this, I get n plus 1 squared times 2 to the n plus 2 times 3 to the n all over n squared to the n plus 1, 3 to the n plus 1. And that's the limit as n goes to infinity. Limit as n goes to infinity. So I'm going to continue to figure out what's happening here. If I have n plus 1 squared over n squared, there's not really anything I can cancel out there. So I'm going to leave that. So I have n plus 1 squared over n squared. The 2 to the n plus 2 over 2 to the n plus 1 becomes 2 in the numerator, and this becomes 3 in the denominator. So if I look at this, I basically have n squared plus 2n plus 1 over n squared and then times 2/3. So if I use pre-calculus methods, I can figure out that the numerator and denominator are basically going to go to the leading coefficients. So this equals 2/3, which is less than 1. So this is absolutely convergent. If I take a look at 3, n factorial over n times 3 to the n. So I have a bunch of non-zero terms. Limit as n goes to infinity of n plus 1 factorial over n plus 1 times 3 to the n. One thing I could have done at the beginning is change this to n minus 1 factorial over 3 to the n. And actually, I'm going to do that to make the math a little bit simpler. So you didn't have to. You could have gone through all the steps, but I'm going to do this. So that's n plus 1 factorial over 3 to the n divided by n minus 2 factorial over 3 to the n minus 1. So that's equal to the limit as n approaches infinity of n minus 1 factorial times 3 to the n minus 1 over 3 to the n times n minus 2 factorial, which is equal to the limit as n approaches infinity. I do a little canceling, so n minus 1 over n minus 2 with the factorials, that's going to be n minus 1 in the numerator, and then I'm going to have a 3 in the denominator. Now notice that the limit as this goes to infinity, n is going to dominate, so this is, the limit is infinity, which is greater than 1, so that means this diverges. Pause it if you need to, because I'm erasing. Okay, number 4, 4 to the n over n plus 1 to the n. So ratio test, 4 to the n plus 1 over n plus 1 to the n plus 1. Limit is n goes to infinity. Now, one thing that I might start to recognize, oh, Jason. One thing that I might start to recognize here is that if I'm doing a problem like this, notice that every single time I've been rewriting it in the denominator, and then I'm flipping the denominator and basically putting it in the numerator. So what I'm going to do is I'm going to put the next term just flipped in the numerator. Oh, and my fault on this. N plus 1 should be n plus 2 down here, because I have to add 1 every time I see an n. So that was my fault. So then this is just going to be 4 to the n. So now I do a little canceling. So the limit as n goes to infinity, it looks like I'm going to have 4 in the numerator, and then n plus 1 to the n over n plus 2 to the n plus 1. That is not necessarily a pretty sight, but I have n to the n plus a bunch of other things. And then in the denominator, I have n to the n plus 1 plus a bunch of other things. And so if I look at that, the denominator has a larger power, and there's no factorial or anything. So the polynomial term is bigger in the denominator. So this is equal to 0, which is less than 1. So this is absolutely convergent. Last test, the root test. Let a sub n, the sum of a sub n, be a series, and we're going to be consistently looking at the limit as n goes to infinity of the nth root of a to the n, and that's going to equal some limit L. This converges absolutely if L is less than 1. It diverges if L is greater than 1 or equals infinity, obviously. And then it is inconclusive if L equals 1. So this is basically the exact same test as the ratio test, except we do some square or cube or nth roots of something. So what we're going to do here is notice that we have series. So let's do the nth root test. So the limit as n goes to infinity of the nth root of e to the 2n over n to the n. I'm just going to simplify this. So this ends up being the limit as n goes to infinity of e squared over n. And if we make n go to infinity, that's equal to 0, which is less than 1. So this converges absolutely. Notice if you have nth powers everywhere, this is a very easy test to do. So the limit as n goes to infinity of the nth root of n over 2n plus 1 to the n, well, that's really simple. So the limit as n goes to infinity of n over 2n plus 1, that's equal to 1/2, which is less than 1. So this converges absolutely. Congratulations, you just learned 10 tests. Oh, I should say that in the plural. You have learned 10 tests. Ask these questions. Does the nth term approach 0? If not, the series will pretty much always diverge. Is the series a special type? Is it geometric, a p-series, a telescopic series, or an alternating series? If it's one of those special types, then you probably want to go for that. Can the integral, root, or ratio test be applied? If it's something that's really easy to do as an integral, and it's not a p-series, or you have the root test or the ratio test, then that might be good to apply. Can the series be compared favorably to one of the special types? So, for example, can you compare something to a p-series and use the direct comparison test or the limit comparison test? Those might be good ideas. All right, pause the video, try these 3 problems. I'll put answers up shortly. Here are the answers to these 3 problems. First, I did the limit comparison test on number 1. You could have done a variety of different things, probably could have done the direct comparison test, but I did the limit comparison test because you could take the limit, it equals 1/2 with 1 over n, and since we know 1 over n diverges, then the series that we're given in problem 1 diverges. Problem 2, I used the ratio test because the terms are non-zero, and when I look at this, the denominator is clearly growing faster than the numerator as n goes to infinity because the power is 1 bigger. So that converges absolutely by the ratio test. And the alternating series test, I know that it does not converge absolutely because the series n plus 1 over n squared is kind of like 1 over n. It's kind of like the harmonic series. So I checked the conditions on the alternating series test. It looks like we have each successive term is getting smaller, and so I proved that that was true. And then I did the limit as n approaches infinity of n plus 1 over n squared, and that equals 0. So because that's true, this was conditionally convergent.